had indirectly mentioned. Thursday, review sheet for the exam. Our exam is next week, next Thursday, not final exam week. Thursday, so 9 days from today is our final exam. So your review sheets come on Thursday of this week. You know, day after tomorrow, you have your review sheets. And the other thing that I wanted to mention about Thursday, well, I think as long as I quit rambling on here, I think we're going to wrap up our stuff today on statistical analysis. That means Thursday, I'll give you the review sheets, we'll talk about your critiques, and then next Tuesday, we'll review for the exam, and then next Thursday is the exam. So we're wrapping it up. It was really nice to have the extra time, and one of the reasons we had the extra time is because as a compliment to you folks, you've just been mastering this stuff on the statistical analysis really quick. I mean, I apparently had really needed a lot more time last go-around when I did this for the class to, you know, absorb everything, and we've just been very efficient and really absorbed these things, you know, quite quickly. I think those are the main things that I wanted to mention. Oh, no, there's one other thing, and this is in response to an email I got from Jordan, and this is going to please everyone. In the syllabus, I had identified a possible extra credit opportunity. Didn't I say that was possible 10 points extra credit? Is that, I didn't clarify that? So, what that was going to be was, and this originally is something that we have done quite a bit in 250, is where people would identify an academic plan. In other words, they would identify, you know, what their major is, what the courses are they've taken, what courses they plan to take, and it's kind of a chance to give you an opportunity to look at what your academic plan ahead of you would be, and me to give you some feedback on that. One thing that makes that a little bit irrelevant for this class is we have so many people that are so far along, including being in outcomes this semester, so many people that are so far along that you really didn't need to do that with your academic plan. Also, if you are meeting with your advisors, at least I know the people, my advisees that's been meeting with me, you know, you should have a real clear idea in terms of that academic plan anyway. If you do want some input on academic plans or something like that for your own personal advising needs, you know, feel free to come see me or your advisor. So, what does that mean in terms of the extra credit? It means that it would be silly to do now. You don't need another paper to write. I don't need another paper to grade, and so I'm just going to give it, but it wouldn't be fair to take away that opportunity because it was in the syllabus. So I'm just going to blankly give everybody the 10 extra credit points as though you did do the extra credit question or the extra credit problem. I saw some, was that your expression I saw a minute ago? Like, oh no, I can't get that 10 extra points?
Well, no, but like everyone in here is a senior and I'm only a sophomore, so that's kind of why I took this class, because I thought we would play it out the whole rest of my career, but whatever.
If you want to do that, come see me and I'll just do that with you.
No, it's fine.
Okay, so I'll be happy to do that with you.
I just feel like a little kid.
But it did kind of become irrelevant anyway, so it wasn't, you know, if we had people like in their second semester of the major or third semester of the major, which technically you're supposed to be before you take this class. And now you guys have really gotten off easy because one of the things that we're really going to rigidly start enforcing as of next year is that tiered thing in terms of prerequisites, where you have to have had 250 before you get into the upper divisions, no more than one upper division course prior to taking 250. So up to now, people have been able to sort of slide around that requirement, and so it's not really relevant to you, assuming that you don't have to retake the class, but I don't think that's very likely. But that is something that's going to be enforced in the future. The other thing that is going to be enforced in the future is people not being able to take outcomes assessment until they have finished the majority of their curriculum and those kinds of things. So we're just getting a little firmer with that stuff.
Yeah, that, I don't know, that kind of struck a chord with me because my situation was, it was really easy to get into this class, but I was in PR before, and I took PR, I think it was 250. It's basically the same class, just in the PR department.
And they do a lot more on surveys and focus groups.
And I was pretty far along there until I switched over to comm. How would that work if would I not be able to take my upper level comms even though I would have to wait until I come back and take 250, or?
Technically, well, it's not going to matter for you.
I was just curious because that's
technically you would have to have finished 250 before you would take more than one upper division course.
Oh, okay. Yeah. That'd be kind of tough on anyone in my situation next year.
Yeah, now there might be some exceptions, you know, that could be made, but yeah, okay. Okay, so when you're you know, you can easily figure your grade up to this point. I mean, right? The only thing that you would not know are your 10 participation points, but you could probably estimate what you would consider to be your class participation points. And all you need to do, if you're in any doubt about how to figure what your exact grade average is, which will tell you exactly what you need on the final exam to get whatever your target grade would be, take your total number of points that you have obtained, divide that by the total number of points that would be possible at this point, and whatever the result is your percentage in terms of what you have. So you know exactly what your grade is. Okay, let's wrap up our significant stuff. I think we'll be able to do today. Again, where we left off way back when, actually, let's do even broader. We had identified our types of statistics. We did all the descriptive sorts of statistics. We got into inferential statistics, and didn't we have that identified as big number 2, inferential? Okay, and so those are our things. This kind of gives you the overall outline. We did all of our stuff on inferential statistics. Our A under here were all of our things on estimates, which included our normal distribution curve, and then we also did our 2 non-normal distributions, both in terms of kurtosis and skew, and we had identified the peak, flat kurtosis, and the positive and negative skew. And then we got into the concept of significance, at least in terms of significance concepts. And here's where we get our confidence intervals and our p-values, and I think we might have talked about degrees of freedom and those kinds of things here. And then we got into significant differences. And here's where we actually started getting into our statistical tables. Remember, in addition to not having to memorize any formulas, I also said that you wouldn't have to memorize how to figure out your degrees of freedom, because your degrees of freedom are on your tables, how to compute the degrees of freedom. You have to be able to understand what that means. I mean, if it says something like, for a one-way analysis of variance, the degrees of freedom are j minus 1 over n minus j, you have to know what that means. But in terms of the formula for the degrees of freedom, that's something that, you wouldn't have to remember. I had mentioned this just a little bit ago, the most complicated formula that you would have to read on the exam or the quiz on Thursday would be standard deviation. Mean, median, mode, and standard deviation are the only things that you would actually have to compute from a sample. Median and mode is not really a computation, that's just kind of looking at it and figuring it out. The mean, would be a computation. When I say the standard deviation, that also kind of implies computing the variance, because, basically the standard deviation is just the square root of the variance. So you're really computing the variance and then just square rooting that to get your standard deviation. Now, there may be an extra credit question on something like a chi-square or something like that, but that would be as complex as it got. Under significant differences, we did our chi-square, which is for nominal data. We did our analysis of variance, our F-test actually, and we talked about a variety of F-tests. Mainly we focused on the one-way analysis of variance. We did talk also, though, about the multiple analysis of variance, the MANOVA. We also talked about the factorial analysis of variance. Remember there, and again, this is reviewing stuff, the distinction with the one-way analysis of variance is you can only have one independent variable. You can have as many groups in that, as you want, but you still only have one independent variable. The other thing we did there with significance test differences was a t-test. And remember, one of the big differences between the analysis of variance and the t-test is, in your analysis of variance, your groups do not have to be the same size, but in your t-test, they do have to be the same size. And then the other thing, and I'm backing up a bit, but the other thing that we did with chi-square, in addition to the single sample chi-square, we also had talked about the cross-tabs or contingency table analysis, which is a chi-square where you have more than one independent variable. And that's where we left off right before Thanksgiving. And then that leaves us our final type of inferential statistic, at least what we're covering in here, which is looking at significant relationships or associations. And again, like we were mentioning a variety of times back when we were doing this stuff before Thanksgiving, these kinds of things with significant differences and significant relationships and associations, these are the sorts of things that relate back to what we were doing early in the semester. If you've got a question or a hypothesis of difference, these are the significant tests that will answer those questions or will prove or disprove the hypotheses. If you've got questions of association or relationship, or hypotheses of associations and relationships, these are the kinds of tests statistically that will prove or disprove those hypotheses or answer those research questions, those kinds of things. So this is relating back to how you would actually answer those questions or prove or disprove the hypothesis. When we're talking, I'm mainly going to focus on interval and ratio data, but I do want to at least mention some relationship possibilities statistically with ordinal data and with nominal data. Your single most common, and this was probably used in some of your critiques as well, your single most common type of statistical test for relationships or associations between variables. Now remember, you're not determining any kind of causality here. You're just saying that things were related or things were associated. And a bunch of you, or at least some of your critiques, I know they were looking more at relational kinds of associations. Your single most common is a correlation. And there are different types of correlations. The main one that's most commonly used, and this is the one we'll go into more detail here, is a Pearson correlation. It's actually referred to as the Pearson product moment correlation. And your statistical symbol for your Pearson product moment correlation is a little r. So when you're looking at a correlation and you see r equals, little r equals, that's your correlation statistic. Let me mention a couple of things first. As I had mentioned, the Pearson product moment correlation is using only interval and ratio data. It cannot be used on ordinal data or on nominal data. It's only for numerical, interval, ratio kinds of data. I don't want to presume that everybody understands what the values and the probabilities are with correlations. Your R values and correlations are much smaller than the kinds of things that we were looking at with like chi-square and the F values and the T values. When you're looking at a correlation statistic, a 1.0 or 1.00 is a perfect correlation. You can never, ever, ever go beyond a 1.00 in a correlation, because that's an absolute perfect one-to-one correspondence in correlation, and you can't get any more than a perfect correlation. You will almost never, ever find a 1.0 correlation unless you're essentially comparing two things that are virtually identical in terms of the way that they would relate to each other. Typically with correlations, you could have, in a range of values, but they're going to be anything 1.0 or less, or it could be a negative 1.0 or greater. The difference in the positive one or the negative one is the direction of the correlation. Remember, we had talked about this early on in the semester in terms of, we were phrasing it as positive and negative associations, but essentially we're talking about positive and negative correlations. A positive correlation is when you have two variables, let's start off with a simple one. Let's not worry about a multiple correlation yet. We've got variable X, variable Y. In any kind of correlation statistics, your two variables or two scores here do not represent two different groups like they did with our F test or our T test or something like this. Your two scores are two scores by the same people, by the same subjects. So if you're correlating, for example, what somebody's score is on a self-monitoring scale with what their score is on a communication apprehension scale, that's your X and Y. It's all for the same people, though, and the same people take the self-monitoring scale, they take the communication apprehension scale, and what you're doing is you're correlating those two things together. So when you're using the correlation here, you're not correlating two different groups together. You're correlating one group in terms of how associated or related two different variables are. Now, it doesn't always have to be with people. I mean, some of your critiques maybe even gone into some of these things. You can be correlating other types of things as well, like maybe with box office success or things like that. I don't know if they used correlations in there offhand, I don't remember. But, you could use other kinds of data to correlate. It wouldn't always have to be people, but at least the sample, though, it would be two different variables that apply to the same thing. So, positive correlation means that the two variables, what's the relationship between the two variables in terms of their directionality?
We're positive?
Yeah.
When one goes up, the other one goes up.
Yeah, or down and both go down. In other words, when you're talking about a positive correlation, both variables move in the same direction. And it could be both going up together, both going down together. So, back to my example of self-monitoring and communication apprehension, it would not be surprising, it would be a reasonable hypothesis to say that there's probably a positive correlation between self-monitoring and communication apprehension. High self-monitoring is the tendency to look more externally, like what are other people doing, what do other people think of what I'm doing, how does my behavior compare with other people's behavior, and then communication apprehension, how nervous or anxious somebody is about communicating. It would not be surprising that people that tended to have high degrees of communication apprehension probably tend to look more externally in terms of what do people think, how do I compare to what other people are doing. If somebody works the other way as well, people that have lower communication apprehension, probably less likely to be focused in, externally in terms of their focus of attention. Now keep in mind though that none of these correlations mean causality. It doesn't mean that if you are a high self-monitor, you're definitely going to have, communication apprehension. There's a lot of times we're just externally focused and it has nothing to do with communication apprehension at all. So by saying two variables are associated, in no way say that they're causal related. It doesn't mean being a high self-monitor causes you to have high communication apprehension any more than having high communication apprehension causes you to be a high self-monitor. It just means that there's a tendency, when you look at those two scores, that they seem to move in a similar direction. But remember, correlation does not prove causality. We went through a bunch of examples earlier in the semester. One of the examples I really like using a lot is, and actually one of the studies, whose study did television violence, exposure to aggressive behavior. That was yours, yeah. And they used correlations, didn't they? Yeah. Well, but those kind of studies are so often, and not that this applied to yours, but those kind of studies so often are taken out of context because what they do is they find that children that tend to watch a lot of aggressive media also tend to behave more aggressively. That doesn't mean that watching aggressive media makes you behave aggressively. It's just as likely that people that are more aggressive in their behavior are more likely to watch aggressive media. It doesn't mean that one thing causes the other. It just means that those two things are associated. So it doesn't in any way show causality. It just shows that there's a relationship. Same direction then. They could both move up together or they could both move down together. A lot of times people think down is negative, up is positive. It's a matter of do they go in the same direction or different directions. Negative correlation then is obviously what? Yeah, there's an inverse relationship, exactly. As one goes up, the other goes down, or as one goes down, the other goes up. Stick with the example of communication apprehension. It would be reasonable to expect a negative correlation between the amount of speaking experience somebody has and their degree of communication apprehension. Doesn't that just make sense that as you have more speaking experience, you would expect that to be associated with lower degrees of communication apprehension? As somebody has less degree or less amount of speaking experience, that is likely to be associated with higher degrees of communication apprehension. But again, that doesn't mean that they're causally related. That just kind of shows you what the association is. So you're never going to find, or at least I can't imagine finding, except in very rare cases, a perfect 1.0 correlation. So your R values are typically going to be small compared to some of the R values that we've been looking at in terms of what you actually look for when you're looking at statistical significance. When you're doing correlations, your degrees of freedom, n minus 2, what's the difference again between big N and little n?
Big N is all the numbers, or all the categories together. Yeah.
Little n is the number of people in one specific group. Big N is the total number of people. So keep it. This is a point though where that becomes somewhat of a moot point because when you're dealing with correlations, let's say you have 10 X scores and 10 Y scores. That doesn't mean you have an N of 20, right? Because it's still the same 10 people. It's just all 10 people took, this score and they took this score. So for example, on your worksheet, when you look at something like sample 8 down there, these X and Y scores, these are from the same 8 people. So your in here would be 8, not 16, because that only represents 8 people. It's just that each person did 2 scores. So our degrees of freedom for number 8 then would be what? I mean, you've got 16 scores, but keep in mind that it's 8 people, each of them taking 2 different scores. So our N is 8, and if the degrees of freedom are N minus 2, then, 6 would be our degrees of freedom. Just for fun, do you wanna work through that sample? I mean, we don't need to, but how many of you have your calculators with you? Does that mean that nobody on this left side does?
Do it in your head.
Just for fun, just to show you that this is not that complicated of a thing, when you're looking at doing a correlation. What would this mean? What does this mean up here? Again, these are symbols that you already know. The sum of x times y.
Over the square root of the sum of x squared times the sum of y squared.
Okay, so yeah, and it's a pretty simple thing, I'm just step by step. So just real quick, if you don't have your calculator, you can just kind of follow along with us. So if you look at number 8, you've got 8 individuals, each taking 2 different scores, and you've got what their scores are on each of those. So your very first step would be go through, multiply the x score times the y score for each of the 8, and then just add that up. So we'll just we'll do it step by step. Some of these you wouldn't need to really, even the calculator for to do part of it now when you get to a certain point you're going to. So the first thing we're doing is adding up our sum of x, y. You just simply go through here, multiply the x times the y, right? So you get 32, 21, 36, 10, 18, 24, 56, and 55, right? If that's just going through, that gives you your top part of the equation right here. Now when you add those up, what do you get? What do you get? 252, right. So our sum is 252. So up here at the top, we have 252. Everybody see how we got to that point? Now our next part, just by step, we want to take the sum of all the x squared. So this is our x, this is our y. So you simply go through, square each of the x's, right? Which is going to give you 16, 9, 81, 100, 4, 64, 146. Is it 146 or 196?
196.
196. And 25. See what we did there? We did this part right here. We simply squared each of our x scores. Now our final thing is to add them up. What do you get when you add all those up? 495. 495. So we've got 495 is our sum of x squared. Now we do the same thing for our y. Square all of our y's, 64, 49, 16, 1, 81, 9, 16, 121, 357. So what we did here, first we squared each of our x's, added them all up, got 495. Squared each of our y's, added them all up, we got 357. What's the next thing that we would do? Well, first probably want to multiply these, right? Because you've got to multiply the 495 times the 357. This would be one you probably wouldn't do in your head.
176,715.
Yeah, exactly, 176,715. What's our next step?
Divide 252, now
Square root that first. What do you get as the square root of 176,715?
120.37.
Don't you actually get 3748?
Yeah.
So you actually round that up to 38, and the reason is because your 8 would round the 4 up to a 5, and the 5 then would round your 7 up to an 8. So it actually would come out to be 420.38. Now that would be an insignificant difference though in terms of, you know, whether you rounded it to 38 or left it at 37. So our final step then to get our correlation, 252 divided by 420.38. What's our R value? 0.599. Now, go to your statistical tables. And I think we discovered that mine was put together in a different order than yours. What you're looking for is the one that says critical values for the Pearson R at the top. I think that might be your last page. Is that right? See degrees of freedom over on the left column. Degrees of freedom n minus 2. What's our degrees of freedom again? 6.
How did you get that?
Pardon?
How did you get 6?
Degrees of freedom n minus 2, and we've got 8. 1, 2, 3, 4, 5, 6, 7, 8. Remember, the two scores are the same people. So we only have 8 people. Yeah. So your n minus 2 would be 6. Degrees of freedom 6. Now the way that you actually write this out, you write R underlined, and then in parentheses you put the degrees of freedom equals 0.599. P is what? What would the p value have to be significant at the 0.5 conventional level? 0.7067. It's obviously not significant at the conventional level, so immediately we know it's not significant. Is it even close to being? Is it even close to significant at the 0.10 level? Doesn't meet that. I mean, it's close, but it doesn't meet the criteria. Because to be at the 0.10 level, it has to be 6215, and it's not 6215. So what would you write? You could write it like we said before. You could do two different things. You could say P is greater than 0.10, which means it's not significant, or you could just put NSD, which means, actually you wouldn't put NSD because that's talking about difference, but just by putting it greater than 0.10 would mean that it doesn't reach conventional level of significance. Now, actually, a 0.59 is a pretty strong correlation if you had more subjects. The problem is, and I think you kind of figured this out already by as many times as we've used the tables, the more subjects you have, the easier it is to reach significance. You know, whatever the value is, I mean, whether you're talking about a chi-square, an f-test, a t-test, a correlation, you could take the same numerical value, and if you have more subjects, it could be significant, whereas the same numerical value for fewer subjects isn't significant. You probably noticed that, because as you look down the numbers on any of these charts, the more degrees of freedom you have, the lower the number has to be to reach significance. So a 0.59 is not significant here because we only have 6 degrees of freedom. What point in terms of degrees of freedom would our 0.59 be significant? What would our degrees of freedom have to be for this to be significant at the 0.05 level? 10, right? Look at 10 degrees of freedom, 0.05, 0.5760, right? That would be significant. So if we had just 4 more degrees of freedom, 4 more people in the study, then this same value would be significant at the 0.05 level. I probably should have gone into that in a little more detail beforehand, but it's a pretty easy thing to grasp now, that the same numerical value with more degrees of freedom, more subjects, more observations, it's easier to reach significance. The same value might not be significant in one case, but if you had the same value and you had more subjects, then that could be significant. This is a classic example. If we just had 4 more people, 12 people total, n minus 2 would be 10, then it would be significant at the 05 level. What some researchers might do, they would do, now you're never gonna do something with just 8, I mean, I'm just keeping it manageable here, but they might do something like do a calculation, they see it's not significant, they might keep that data and then add some more subjects into the study doing the same thing, and if you get the same numerical value for these extra subjects, now all of a sudden it might be significant because you've increased your degrees of freedom. So it's just it's a way sometimes of just sort of not giving up just because you don't find significance, right away. It seems like you've got the concept and kind of following along pretty well. On your second page then, down at the bottom, number 5, Pearson product moment correlation coefficient, 50 subjects. We've got, what we're doing here is we're correlating, or at least hypothetically, the SAT, which is, now in Michigan, you actually take the ACT, maybe you don't take the SAT. It's similar, it's a scholastic aptitude test. A lot of universities in states where they give high school seniors the SAT, they use that as an admission standard, or partly as the admission standards for getting into college. And the rationale is that you're expecting that people that score higher on the SATs are more likely to succeed in college. And so you take the 50 subjects' SAT scores and you correlate that with what their second year college grade point average was. The prediction would be that there should be a significant correlation. What's our N for this hypothetical study in number 5? What's our degrees of freedom?
40.
If we had a correlation of 0.41, what would be the significance, or would it be? Now you go back to your tables. So here are degrees of freedom are 48. We've got R, 48 equals 0.41. Is it significant? Remember, you always round down when you're looking at the degrees of freedom on your charts. What is the most significant, as you're following it across, what's the most significant confidence, interval confidence that you could claim? What? 0.01, right? P is less than 0.01. So again, we're looking at our degrees of freedom of 48. You don't have 48, it goes up to 45, then it goes to 50, so we round down to 45. We always start at the 05 level. It only has to be 0.2875, so it's obviously significant at the 05 level. It's even significant at the 02 level. You look all the way over to the 01 level, 0.3721, it's significant there. So we go ahead and we look at the 001 level, 0.4648, it's not that high. So we go back to the most significant, which is 0.01. Everybody see where we just got this? This is a good example of what I was just explaining in terms of your number of observations. Remember just a minute ago with our sample, a 0.599 correlation was not significant because we only had 6 degrees of freedom. Here we actually have a lower R value, it's only 0.41, but yet it's significant, not just at the 05 level, it's significant all the way to the 01 level. And it's because we have higher degrees of freedom. We've got 48 instead of having 6. Again, this is much more realistic. You're hardly ever going to find people trying to prove a statistical correlation when you're only looking at, 8 samples, that kind of thing. Everybody see where we got this? What about on the second example? What if the correlation was 0.24? Yeah, P is greater than 0.10, because again, obviously you see when you're looking there that it has to be 2875 at the 05 level, it's not that big. 2428 at the 1 level, 0.10, it doesn't even reach that level. It's close, right? But we can't add that extra 228 in there. So actually, as close as it is, we have to say that it's greater than 0.10, which means it's not statistically significant. I not follow anything? So, Jordan.
Yeah, I don't kinda get that at all, the P part.
Well, I mean, in general, you understand that from all the stuff we did before.
Well, kinda like, I just don't get where you get that number this time, man.
Okay, well, doing the same thing that we did with the other ones, you know, if you're looking, our correlation, like for this one, for example, our correlation was 0.24, the R value. Our degrees of freedom are 48, so when you go to your table, you look at 45,
Oh.
then you look over and you see to be significant at the 0.10 level, or to even be at the 0.10 level, it has to be 0.2428. You see where we get that number?
Yeah.
You see that? Okay, and it's not 2428, so we have to say it's greater than 1.0, which means it's not significant,
Okay.
or 0.10, not 1.0. So, summarizing with Pearson product Bowman correlation, key issues. I mean, understanding the concepts are much more important than actually, you know, computing it. That was just a sample to show you that it's not as complex as what sometimes it seems like it might be. It's a measure of significant association or relationship, not saying anything about causality, just simply saying these two things tend to be related, or these two things tend to be associated, but you can't say anything about causality from simply having a correlation. It just means there's a relationship. And I don't need to go into the detail, but for any of you that ever read some of this stuff, it's just phenomenal, some of the things that when you actually did statistical correlations, some of the things that do come up statistically correlated, when you know that there's no way, you know, that there's actually a relationship or causality between those two things. So it's for interval and ratio data. It's the little statistical symbol R. When you see the little R, that means correlation. Positive means they go in the same direction, up or down. Negative means they go in opposite or inverse directions. A 1.0 is a perfect correlation, so your values are less, you know, I mean, where like we just had with, you know, with 0.41 that turns out to be statistically significant. You're dealing with a different kind of standard there. Let me just mention a couple of other types of correlations without going into the detail or the depth or anything like that, and that's just to be consistent. You do have, when you're looking at ordinal data, again, the Pearson product moment correlation is the single most common correlation that's used when you have interval or ratio data. You do have another type of correlation, though, called the Spearman-Rho, and this is when you're dealing with ordinal data. In other words, remember what ordinal data is? It's where there is some hierarchy or relationship between the variables, but it's not an equal interval. You know, somebody would say something like, rate your 5 favorite comedies on television in order, rate your 5 favorite dramas on television in order. Well, I don't know what you'd get out of correlating those two things. Maybe there would be something, maybe there'd be some relationship there. But that would be ordinal data, and so a Spearman-Rho would be a kind of correlational statistic. It's much easier to compute than our Pearson product moment correlation is. It's the kind of thing that you would correlate that just shows, is there a relationship or an association between your rank ordering of things. Again, I could see some things maybe where this might apply. It would be an interesting one, for example, if it was the early stages of an election, and you said something like, rate your top 5 candidates for the election in order of preference, rate your top 5 sources of news about the campaign in order of preference. That might be actually a fascinating correlation if you found that the preference people had for their candidates was related to the preference in terms of where they get most of their campaign information. So there could be some cases like that where it would be really interesting. You couldn't use a product moment correlation, though, Pearson, because there's nothing about the ranking your top 5 choices for candidates or your top 5 choices for news sources about the campaign. There's nothing about that that's interval or ratio. It's just the order. And there is one other one that's worth mentioning as a point biserial correlation. And point biserial correlation could be used on nominal data. It can also be used on ordinal data as well. But again, it's a whole different kind of thing, because remember with nominal data, you're just dealing with categories. You're not dealing with any kind of hierarchy or relationship at all. But your point by serial correlation could be done with nominal data, or it could be done with ordinal data as well. So I just wanted to mention those so you know that there are ways of measuring for associations and relationships when you're not just dealing with something like interval or ratio data. Questions on our correlations? The concepts still apply though, in terms of, you know, of one being a perfect correlation, positive correlation, negative correlation. Even if you're talking about the Spearman row and the point by serial, all that stuff we were talking about initially, that applies to all types of correlations. A one is a perfect correlation, positive means they go in the same direction, negative means they go in inverse directions. That applies to all kinds of correlations. Another main type of statistical test for associations or relationships, and this one actually has a lot more statistical power than your correlations do, because not only are you showing a relationship between two things, but you could actually be making predictions about things. You have a criterion variable and a predictive variable, or a prediction variable, and that's a regression analysis. Regression analysis is still a measure of association or a measure of difference. Oh, wait, before, save space real quick. There's something, I knew I was overlooking something with correlations. We're gonna get to regression analysis in just a minute. One thing that I didn't mention, or actually two real quick things that I need to mention about correlations. One is it is possible to have multiple correlations. Multiple correlations are where you're correlating more than two variables at the same time. What we did with the Pearson product moment correlation, that was just two variables. You know, we were only correlating two variables. You can correlate more than two things though at the same time. You could correlate three, for example, and there's some good kinds of examples of research where they actually correlate three. So a multiple correlation is where you're correlating three or more variables at the same time. Is there a relationship? And I'll just give you an example of sometimes where a multiple correlation is useful. If you're trying to figure out how much of a factor some individual variable might play, and I'm thinking of a particular study here that did this, you might start out by just correlating two variables together, and you get what your correlation value is. Then you add in your third variable and do a multiple correlation. If your correlation is higher, then what that means is that third factor is contributing to your overall correlation, because when you add that third factor in, you get a higher correlation than when you don't add the third factor in. Can you see the logic and the rationale? If we did a correlation with two variables, variable x and variable y, and we got something like a 0.51, and then we do a multiple correlation, and we include variable x, y, and z, and our correlation turns out to be something like 0.78, then what that means is, when you factor in variable z, you're actually getting more of a higher correlation, which means it is a contributing factor there. And just comparing those two things is a way you can kind of assess how much does variable z really contribute here. Do you see the rationale? Do you see what I mean? One other thing to mention with correlation is, and this is an example of a type of multiple correlation as well, and that's the idea of a correlation matrix. A correlation matrix is where you plot out multiple correlations. For instance, if you look on your last page of the tables and charts handout, it looks like the second page, actually I think it looks like this on your last page. Your first page isn't going to look like this. Your last page is. Now it's not going to have all the green and stuff on it. Up in the upper left corner, that's a correlation matrix. What you really have here is a multiple correlation of 7 different variables. It's showing how each variable correlates with each of these other variables. And so really what you've got when you look down the vertical side, you know, the vertical axis, you've got 7 different characteristics of relational communication: talk embeddedness, number of encounters, topic breadth, you know, breadth means the range of topics, satisfaction, importance, effectiveness, personalness, you know, how intimate or personal the communication is, And then when you're looking across the top, you see the numbers 1 through 7 again, those represent the same 7 variables. So really what you've done here is you've looked at how every one of these variables correlates with every one of the other variables. So for example, is there, oh, and then a lot of times when you see the correlation matrix, they will asterisk any of the correlations between variables that reach a level of significance. Here, the asterisk represents significance at the 0.5 level. You can see that at the notation under the table. So what is the correlation between encounter satisfaction and encounter importance? Just follow it until the two meet. 0.64, you see where she gets that? Encounter satisfaction is number 4, encounter importance is number 5. So look at number 4, encounter satisfaction, follow that over until you get to the number 5 column, which represents encounter importance, and you see this 0.64. Is that significant? Yeah, I mean,
Yes.
you see the asterisk, you see it's significant at the 0.05 level. What's the correlation between interaction personalness and number of encounters? 0.20. Number of encounters is number 2. Follow along all the way to number 7, which is the personalness, and you see 0.20. Is that significant? Yeah, not as high as the other one was, but it still reaches a 0.05 level. Why is there nothing on the bottom part of the chart? Yeah, that would just repeat everything that's in the upper right. What's the reason for the dashes there that you see?
The same.
Yeah, that would.
Between two things that are the same and
Yeah, exactly. I mean, that would be correlating number 1 with number 1. That's where you would have a perfect correlation if you're correlating something with itself. Anybody not follow what we're doing here with the correlation matrix? Give you a good applied example of where we've actually talked about this, but without going into the detail. Remember back in the second unit when we were talking about, or actually this was our first unit, and we talked about it a little bit in the second as well. Inter-item correlations as a measure of reliability. When you have a questionnaire, and one of the ways of assessing reliability is you do an inter-item correlation, which is where you correlate every one of the items with every one of the other items. This is exactly what you end up with here. Different things included, but what you would have an inter-item correlation. You have, let's say, 10 items on your questionnaire. You have them listed 1 through 10 on the left side, and then you have 1 through 10 across the top, and that will tell you how each item correlated with each other specific item. This is exactly what an inter-item correlation would look like when you actually computed it and how you lay it out. And then you could just look at the table, look at that one table, and it would tell you every single correlation for every one of those factors with every one of the other ones. You feel pretty confident to be able to read this? Because this is something you would need to do if I, like you'd have a sample of a correlation matrix and I would ask you something like, what's the correlation between these two factors? All you need to do is just look at the chart. Everybody see how we got those? Okay. Now, we'll move on to our other type of association, which is regression analysis. Regression analysis, as I said, is a stronger measure of association. It's a much more rigorous statistical test. And essentially what you're doing with the regression, keep open to the page that you're on, because the rest of what's on that last page there deals with regression analysis. You've got your X and your Y variable, but you actually you're trying to make a prediction. The reason for doing the regression analysis a lot of times isn't just to plot what a relationship is, like the correlation does. It's actually, if you reach a strong enough regression association, then it's a way that you could use one variable as a predictor of another variable. So a lot of times when you're, and again, that's why this is inferential, a lot of times when you're doing a regression analysis, you're really getting a twofold kind of thing. One thing that you're getting is what's the relationship between the variables. The other thing that you're getting, though, if it's a really strong relationship, that would tend to indicate that you could use one of those variables, bless you, as a predictor of the other variable. The variable that's along the left axis, what would be your y-axis, the vertical side, that's what's called your criterion variable. And your criterion variable is the variable that you're trying to predict. The x-axis along the bottom, the horizontal axis, that's referred to as your predictor variable. And your predictor variable is what you'd be using to predict the criterion variable. So, wouldn't that make sense? Just, I mean, take this example here on your handout in figure 14, 14.6 or 14.8. Top of line's cut off. In any event, you know what we're
6.
talking about. Is 6 in the upper right-hand column. Your x variable, your predictor variable, is minutes per day spent watching television news. Your variable y on the left vertical axis is the amount of knowledge you have about current events. Can you see why that would make sense in terms of the predictor variable or the criterion variable? In regular language, what would this tend to say? This is a real strong relationship. Now, we'll talk about the specific types of relationships, but this one really does come out to be a very strong relationship. So, aside from saying there is a strong regression relationship between knowledge of current events and the amount of time, minutes per day you spent watching television news, since we can also use this as a prediction, what would you say then this would lead us to? What would be our conclusion?
The more you watch television, the more knowledge you have of government.
Yeah, and it's not just the association, but you could actually say that the amount of minutes per day you spend watching television news could be a predictor of how much knowledge you have about current events. And what gives you the strength of the regression analysis is how clustered they are around a certain individual pattern. For example, when you're looking at this sample that we're looking at here, what you're really looking at here is a positive linear relationship. Now, in a moment, I'll make the distinction between a linear and curvilinear or quadratic relationship. But it doesn't always come out in an exact line. Where you see all those dots, those would represent all the individual scores. But if you see that all those individual scores tend to follow along a pattern, then what your statistical analysis shows you is, if that's a significant relationship, it means that, there's a linear relationship there. That as you spend more time watching television news, your knowledge of current events goes up. And that's a pretty strong relationship. So all the individual dots simply represent individual associations for your individual subjects. How much time do they spend watching TV? How much do they know about current events? But when it tends to follow along a pattern like that, that's when your statistical analysis would show that it is a significant regression relationship. If, on the other hand, instead of following along a pattern like that, your individual dots were just kind of randomly all over the place, you'd say there is no relationship between those two things at all. You can't use your amount of minutes per day watching television news cannot be a predictor variable for how much knowledge do you have about current events. Jordan, did you?
I was gonna ask you to repeat what they are, because I wasn't really.
These two?
Yeah.
The criterion variable is the thing that you're trying to predict, and the predictor variable is the thing you're using to predict it. So back to this example, the criterion variable is your knowledge of current events. Your predictor variable is the number of minutes you spend watching TV news. So the rationale would be, can we use the amount of time you spend watching news as a predictor of what your knowledge of current events would be likely to be? This is exactly the example that we have mentioned a couple of times in class with things like the SAT or the ACT and the GPA. The idea is that your college grade point average would be your criterion variable, and the SAT score or ACT score would be your predictor variable. What does that mean in regular words? It means that, theoretically at least, now we know that there's limitations and this actually doesn't turn out to be true all the time, theoretically that your SAT or ACT score in high school should be a reasonably good predictor of what your college grade point average is going to be. Same kind of thing holds true theoretically with the GRE, the Graduate Records Exam. You know, the idea is theoretically that your score on the Graduate Records Exam should be a reasonable predictor of how well you're gonna do in graduate school. Now, what has really come to be the case, because these kinds of things have really been studied quite extensively, and they don't always reach any kind of significance, and there's even differences. I don't know why this is, I even mentioned this before in class, I think, that the correlation between SAT and college grade point average is actually lower for females than it is for males. Why would it be a better predictor for males than it is for females? And you get all kinds of problems and issues with that. Essentially, what the GRE and the SAT and the ACT have come to be is just another way of weeding in and weeding out people for admissions. If you've got a really competitive graduate program, you can't accept everybody that applies, and the GRE just gives you another factor that you can use in terms of these are the people we'll accept, these are the people that we won't accept. Now, universities like Northern are pretty easy to get into regardless of what your SAT or ACT scores are, but for universities that have much more stringent standards in terms of admission, the SAT or the ACT scores would be a big issue. And again, they would just have a cutoff point. If you don't meet this minimum, you're not even considered for acceptance. You know, so it's just it doesn't really mean it's a reliable predictor, it's just another way, you know, in actuality that they use to be able to weed in and weed out, you know, especially when you're dealing with universities that have real high admission standards and they have a lot more people applying than you could possibly accept. Well, that tells you in general what regression analysis is. Now you do, when you're looking at the relationship between the variables though, between your criterion and your predictor variables, you've got two broad categories of types of relationships. A linear relationship. A linear relationship is where they tend to go in a reasonable straight line associated with each other. And you could have a positive linear relationship or a negative linear relationship. So if you look down in the middle section of the handout on the far left, this would be just like we had with our sample we just did with amount of time watching news and the amount of knowledge of current events. That's a positive linear relationship. But same kind of thing as with correlation. As one variable gets larger, the other one does too. As your number of minutes increases watching news, your knowledge of current events gets larger as well. Same concept as with a correlation. This is also the theoretical relationship between things like SAT scores or ACT scores and college grade point average. Theoretically, the higher your SAT or ACT score is, should lead to a higher college grade point average. Now again, that doesn't mean it always works out that way, but theoretically, you know, that's kind of the rationale. So that's a positive regression relationship. It's linear because they go in a straight line. Now it's always not going to be exactly perfect. I mean, you can see by the dots, but when you pattern out those dots, it's essentially forming a line. So linear means they're going in a straight direction. Positive means they're moving in the same direction. A negative linear relationship still means they're moving in a straight line together, but it means it's an inverse relation, right? As one variable is getting bigger, the other variable is getting small. You can still use it as a predictor, but instead of predicting the bigger this one is, the bigger the other one's going to be, your prediction would be the bigger this one is, the smaller this one's going to be, right? I mean, just envision whatever we wanted to plug in as the variable, just envision a set of numbers here, and envision a set of numbers here. The bigger that the x one gets, the smaller the y one gets, right? If you've got an x of 10, you've got a y of 1. If you've got an x of 4, you've got a y of about a 5. If you've got an x of 1, you've got a y of 10. So you see it's moving in an inverse relationship. This would be a good example of something like, back to an example I used with the correlation when I was talking about the amount of speaking experience being related to communication apprehension. If it was a really strong relationship, so much so that you couldn't just say it's correlated by something like a product moment correlation, but if you could actually show a linear negative regression relationship, you could be saying that we could actually make a reasonable prediction about how much your communication apprehension level would be based on how much speaking experience that you have had. Again, it's not likely to turn out that way, but that would be what it would be if you actually had that negative linear relationship. So linear means they're moving in a straight line. Positive, they're moving in the same direction. Negative, they're moving in the inverse direction. Any questions on the the linear, that's the easy one, I think, the easier one to understand. Your next series of relationships, and there's multiple names that could refer to some of these, and we're not gonna cover every single possibility, we'll just cover the four main ones. And that's a curvilinear relationship, also referred to as a quadratic trend. Quadratic trend means exactly the same thing as curvilinear. It means that you don't have a straight line, but there is still a relationship. But when you plot out the relationship, it takes on some kind of curve. Now you do have multiple types. Your four basic types are identified at the bottom. When you're looking at the two next to your positive and negative linear one, your U-shaped curvilinear and your inverted U-shape, both of those are really just samples of parabolic relationships. You can see, your last one over. And again, the U-shape just means that it tends to go in a U sort of pattern. The inverted U means it tends to go in the other way around. So let's look at something like the U-shaped parabolic relationship. Now these are a little more interesting and maybe even a little more challenging to try to conceptualize. What this means is, up to a point, as the one variable gets larger, the other variable gets smaller, then you reach a point where that turns around, and as one variable continues to get bigger, then the other variable starts to get bigger. So there's kind of a threshold point here where if there's a negative relationship for a while, but then you get to some threshold point, and then it turns around and it starts becoming a positive relationship. Can you think of anything that might, and there's actually lots of examples of curvilinear relationships, can you think of anything that might conceptually fit this sort of relationship? I mean, any real world variables that might follow this inverted or this U-shaped parabolic? You see why I'm calling it parabolic? If you look at the bottom far right, that's when you have the curve like that, that's a parabolic relationship. Can you think of anything? One of the examples I had, and this is possible, this is just a possibility, but you can conceptualize how this might occur. Let's say that we were looking at relationship satisfaction in marriages with the length of years, the number of years that people have been married. Could you see just conceptually what that would mean if we did find this U-shaped parabolic relationship? It means that as the number of years go on, the relationship satisfaction tends to drop down. However, after they go past some critical point, and there's all kinds of sociological information in terms of what number of years a couple is together that makes the biggest difference in terms of are they really going to be together for the long haul, or are they more likely to not to stay together. But after some critical point, then all of a sudden, the longer that they were together, their satisfaction starts going back up. Can you just conceptually at least see logically what that might mean? As the years go on, maybe you're a little less satisfied, and you kind of plateau down here, but after you have that sense of history, more years behind you, more experience behind you, you can see the same thing turning around and starting to go back up. What if you have the inverted U shape, something like this? One of the conceptual examples that I think would be a good illustration here is if you're talking about the sensitization-desensitization relationship between exposure to some kind of stimuli. When you're initially exposed to some kind of extreme stimuli, a lot of times at first, your repeated exposure increases your reaction. You actually become more sensitized, react more the more you see something. But isn't there a point where, actually there is, I mean there's obviously a point, it's a basic psychological process, where extensive exposure to the same stimuli, we start reacting less. And so once you've reached a certain critical number of exposures, then you're going to start reacting less to that very same stimuli. Again, there's just many, I mean, you could, one of the things I think that would really plot out nicely here is if you were doing something like looking at graphic violence or graphic sex or sexuality, implicit or explicit, or even profanity in things like movies or television programs. You could see that as these things started becoming using more profanity, more implicit or explicit sexuality, more graphic in some of the things that were portrayed, you could see people reacting more and more negatively to those. And then after a point, we get desensitized as a culture, and all of a sudden we start not reacting as much. It's just, it doesn't even have to be like in a short period of time. Look at how much horror movies have changed in the last generation. You go back and you look at something like the 1950 scary movies, and they're not scary. Little kids would watch those movies nowadays, and they'd laugh. They wouldn't be scared. Well, they were scary to people in the 1950s, and we're still all human beings. The thing is, though, in today's generation, they're exposed to so much of those kinds of stimuli and so many of those kinds of movies that the way that they used to scare people back in the 1950 movies, that's just not going to scare people anymore. So if you only kept that level of fear induction in scary movies, you would eventually find the culture not being scared by those movies at all, and people wouldn't even go see them. So what happens is, it's a constant challenge in that kind of movie production, because you constantly have to be coming up with new ways to scare people and new things to scare them about, because you can't keep producing the same reaction again and again. Now there might be some classic old, Hitchcock or something in the 50s that could still be kind of scary. Same kind of thing when you're talking about profanity. If you're first listening to profanity on primetime television, you could see that it increases a reaction. After a while, you just get so used to it. You could watch a television program, and if somebody said how much profanity was used in there, you'd say, gosh, I don't really even know. We become so desensitized to it that it really doesn't even stand out that much. So this kind of inverted U shape would be a classic example of something that would be, possibly fall along the lines of like our sensitization, desensitization. And you could probably think of some other kinds of examples that would fall within that particular kind of relationship. So what are both of these, the U shape and the inverted U shape? Both of these are parabolic curvilinear relationships. And again, you see a more simple illustration in the bottom right, but then up above that you see sort of the difference between the U shape and the inverted U shape. Another kind of relationship, we've seen the linear, another type of relationship, I'll move one over to the left before we go to logarithmic, is a hyperbolic. Describe in words what's happening with the hyperbolic relationship. Then there's no effect whatsoever, right? It increases up to a certain point, and then there's a certain point where more of your x variable doesn't change what the y variable is. It does in the beginning. Classic example of this, there's a theory in persuasion that looks at how strong are our attitudes, how intense is our commitment to an attitude based on the amount of information that we consume that supports our attitude. Absolute great example of this kind of hyperbolic relationship. When you first develop an attitude, it's real new and you've just got a little bit of information, can you see how as you accumulate more and more information, your attitude, intensity, and certainty is going to go up and up because you're getting more and more information? But it's not going to continue on infinitely, ad infinitum. There's a point where you become certain enough that no matter how much more information you consume, it doesn't increase the intensity anymore, it just reconfirms what you already know. So if you're thinking conceptually in terms of consuming information that supports our attitude, this would be a great example. As we first get information, the more and more information, it increases our certainty of our attitude. But there is a point where we say, okay, I'm certain about this. And no matter how much more information you get, it's not intensifying your attitude. Classic example, when the idea was first, when you're a kid and you first hear of the concept that the world is round or oval shaped instead of flat, you could see, that developing more certainty and a little more clarity in the kid's mind. But I'm sure that today, if you read a book, a geography book, and it talks about the circular spherical shape of the Earth, the fact that you read new information, you're not suddenly gonna become more certain that the Earth's not flat. I mean, that's something that you already know, and no matter how many sources of information you read that says the Earth isn't flat, you're not gonna continue to be more certain. I mean, you get to a point you're certain enough, and all the extra information you get is not changing anything. The election would be a great example of this, right? For somebody that did not have a lot of political information about the candidates before the election, even though I don't know how you couldn't have a lot of information about President Obama, except there's actually a lot of people that didn't know much about his policies, though, and what he did and how successful he had been in terms of, you know, a lot of his policies. You can see that in the earlier part of the election. As they get more and more information supporting a candidate, you can increase your intensity in terms of how favorable this candidate is, how likely I am to vote for this candidate. Isn't there a point that you make up your mind, this is who I'm voting for? And it doesn't matter if you keep getting a lot more information and a lot more information. If you've already decided this is who you're voting for, more information isn't really gonna make it any different. You can't vote for them twice, you know, something like that. So that's a good example of this sort of hyperbolic kind of relationship. Now, one other kind of relationship that we did not mention is the next one over on the left, which is the logarithmic relationship. At first glance, the logarithmic doesn't look that much different than the hyperbolic. What is different about the logarithmic compared to the hyperbolic? There is a steady increase. What were you gonna say, Erin?
It begins, just like the hyperbolic, but it almost looks like a big parabola, but it doesn't ever go down.
Yeah, here's a way of saying it in language, in words. It's, well, I mean, I've been using sign language up to now. It is still an increasing relationship between the two variables, but the rate of increase decreases. It still increases, but the rate of the increase decreases, if you follow my rationale. So the two variables are still related, but the degree of increase lessens as it goes on, but it's still increasing. Give you a couple of examples. This one actually just came to mind, but there's another one, a couple of other ones that I wanted to mention. When you're talking about things like population growth, a lot of times people get really confused when you're looking at population statistics when they talk about things like the rate of population increase has gone down so much percent in the last generation. Some people mistakenly think that means population growth has gone down. No, it says population is still going up, but the rate that it's going up is less. So it's still increasing, but it's increasing at a less significant rate than what it was. You see the same kind of thing with unemployment, where somebody says, well, yeah, unemployment might be going up, but the rate that unemployment's going up is less than it was so many years ago. Now, those are just examples of the concept that I'm talking about. Those wouldn't really fit here in terms of regression, because I'm only talking about one variable, not the relationship between two variables. What would be a good example of something like this? Actually, for any of you that have some really advanced stereo equipment, a lot of volume controls are logarithmic volume controls. That's exactly what that means. It means that as you're turning, you know, over here would be your number on your volume control. Over here would be the decibels in terms of, you know, decibels is a psycho or an acoustic physics measure of the loudness of sound. And down here are your volume numbers. What a logarithmic volume control means is that as you increase from number to number in the lower numbers, it's creating a greater difference in the loudness than as you increase number by number in the higher numbers. In other words, going from number 2 to number 3 on your volume creates a bigger loudness difference than going from number 7 to number 8. That's what a logarithmic volume control means. It's still, as you get to your higher numbers on your dial, you are still increasing the volume, but the amount of the volume increases relative to the previous number is not as much as it was on the lower numbers. And that's exactly what logarithmic volume controls would mean. Two things that come to my mind in terms of, you know, human subjects, not just the acoustic physics stuff, when you're talking about a logarithmic relationship. One would be language development and age. Doesn't that just conceptually make sense? Without me even explaining it, just by saying language development and age. Age is our predictor variable, our criterion variable is language development. So what does that mean? If we say language development and age, what does that mean in terms of this logarithmic development?
Age or language development gets better, or develops more to a certain extent, but as you get older, you don't develop as much in that area.
You don't develop as much in as little of a time, right? I think all through life, at least up to a certain point, your language development is still going to get better, but your difference in your language development between when you're 30 and when you're 35 is not as much as when you were born to when you were 5. Your language development from 1-year-old to 2-year-old is a lot more than your development from 18 years old to 19 years old, right? You're still developing language, you're learning new words, you know, those kind of things, but the rate at which your language development increases is not as great year by year. I mean, in those early ages of a child's life, you know, every month, you know, is tremendous amount of development. I mean, what goes in the development of a child in 1 or 2 months, you don't have near that much development in 1 or 2 months, you know, as an adult. So that would be an excellent example of a logarithmic kind of relationship. Another good one would be educational level and reading comprehension, right? You know, I mean, just look in the younger years, preschool, kindergarten, 1st grade, 2nd grade, look at how tremendously much your reading comprehension increases year by year, grade by grade in those early years. However, when you get older, is there as much of a difference in 10th grade to 11th grade? Is there as much of a difference in your reading comprehension your 2nd year in college compared to your 3rd year in college, as much as there was when you were 2 compared to when you were 3? So as your educational level increases, your reading comprehension still does increase, but it doesn't increase as much relative to your educational level as it did in your earlier years, those kinds of things. So we've got 2 basic kinds of regression relationships. Linear, of which there could be positive or negative. Curvilinear, of which there could be hyperbolic, parabolic, logarithmic. And it is worth making the distinction when we're talking about the parabolic. You could have the U shape or you could have the inverted U shape, because I did want to be sure that you know, that you were clear on both of those. Just a little side note, when you're looking, if you're ever looking at research where they're trying to answer questions of association or of relationship, or test hypotheses of associations or relationships, if they report regression significance, it is a much, much, much stronger significant relationship than just reporting a correlation. Sometimes people might even start out with something like a regression relationship, and if it doesn't reach statistical significance, they'll back off and they'll do a correlation, because it's easier to get significance with a correlation than it is with a regression analysis. Questions on our curvilinear? Okay, 2 other kind of relationships, just to mention quickly. We don't need to go into as much detail as we do on the regression analysis.
So funny.
Let me, for some of you, this is just not going to be something they pay much attention to, but for others, you might actually find this beneficial. Just as a neat kind of mental exercise, when you do come across literature, you're coming across any kind of information where they're talking about 2 things being related in one way or another, just in your mind, see if you can envision which kind of regression curve or which kind of regression relationship would that be. Particularly fascinating when you think of things and say, gosh, that would be the logarithmic, or that would be the parabolic or the hyperbolic. It's just kind of a neat thing to envision in your mind what those relationships might look like. One other relationship and association that's worth mentioning is factor analysis. Factor analysis is also referred to as cluster analysis. What factor analysis or cluster analysis does is, when you're looking at multiple items, it shows you which items tend to be related or associated together. For instance, let's say that, or cluster together, let's say that we had 20 items on a questionnaire. And a lot of times what you might do is you might want to say, well, are these 20 different things, or are some of these things related to each other in some way or another? What a factor analysis or a cluster analysis does, and it's not going to be this simple, but I'll just say it this way to make it more simple, it's going to say, well, you know, the way that people scored on these 3 items tended to be real similar, and the way that they tended to score on 18, 19, and 20 tended to be real similar. The way they scored on 5 wasn't really similar to anything. The way they scored on 7, 12, and 14, these tended to be real similar. And what that does is it really just increases the depth of your knowledge of the profile of how a set of items might relate to each other, where instead of seeing this as 20 different items, you could say what we're really looking at here are maybe relatively fewer things. It seems like 18, 19, and 20 might really be assessing just the one thing. It seems like 1, 2, and 3 might be assessing the same thing. Same thing with 7, 12, and 14. 5 seems to be assessing something completely different. So it shows you what items cluster together in terms of the similarity in which people answer those. There's a lot of practical uses of this, but one particular really useful place for factor analysis is if an argument is made about a questionnaire. Let's say you have a questionnaire that's supposed to be assessing a particular concept. And remember the idea between unidimensional and multidimensional way back in the beginning of the semester? If you have this questionnaire that's supposed to be assessing something that's unidimensional, and I probably even mentioned something like this at that time, and you say, well, is this really a unidimensional, or are you really assessing different things? They'll run a factor analysis, and they'll say, if you find on your factor analysis that you have these different clusters, then that's a pretty good indication that you're really assessing something that's multidimensional. Because if it really was unidimensional, you would expect all of these to be similar to each other. But if you end up with some of these items clustering together similar, and other items clustering together similar, that's a pretty good indication that this is probably something that's multidimensional rather than unidimensional. Otherwise, you wouldn't see those different, those different kinds of clusters. So it's a great way of assessing multidimensionality in a concept. If you devise a whole bunch of questions that should be related to something, and you find a series of clusters, that's a pretty good idea that each of these clusters probably represents a different dimension of whatever it is that that you're assessing. So it's an excellent kind of test with that kind of situation. One final relationship or association to mention, and that's an analysis of covariance. And to keep consistent with our ANOVA, which stands for MANOVA. Yeah, and the difference is ANOVA is one independent variable, one dependent variable. MANOVA is multiple dependent variables. This is referred to as an ANCOVA, which means analysis of covariance. Essentially, the analysis of covariance is the same type of thing that a correlation is. It's just a different statistical test for showing the relationship. Basically, what the analysis of covariance is doing, and this is a little different conceptually than the correlation. The correlation is just sort of showing what the score is on one variable with the score on the other variable. An analysis of covariance looks a little more at, as one of the variables differs, how does the other variable differ in relationship to it? What you're saying is basically how do they co-vary? As one thing varies, how does the other thing vary with it? It's looking a little more at the different variance in each of the variables rather than just one number compared to one number. Don't worry too much about the depth of the difference between a correlation and an analysis and an ANCOVA. Just the idea that an analysis of covariance is another statistical test of associations or relationships. Your correlations, probably your most common. Your regressions show you relationships, but they're your strongest relationships. Of any of these, the regression is the strongest of all of them. Your factor analysis is to show you clusters of items that may be similar, and your covariance is another way of assessing a correlation, basically. And we won't worry about, degrees of freedom or anything like that. There's really a lot more on inferential statistics that